a potato. You had the potato shit.
No, is it good?
So yes.
All right, y'all. Let's learn. Remember the last thing we did? I explained this idea of using polynomials to approximate like more complicated functions. Like e to the x is the example that I gave. And then we did this one example of a function that we don't even know, but we can approximate it using the function value, the first derivative, second derivative, third derivative. And the idea is that you match the functions like the function's value at 2 for this problem. The function's value at 2, the function's first derivative at 2, the second derivative at 2, the third derivative at 2, and then the more and more derivatives that you match, the closer and closer your polynomial will match the original curve. All right. That's a quick reminder. And then it has us do another couple. It says find the Taylor polynomial of degree n for that function at 2. And so again, remember the idea is that we want to know what's the function value at 2, the function's first derivative at 2, second derivative, etc. How many degrees did it say? Degree n. Okay, so just the general one for any n. So I think the thing to do is take enough derivatives that you see a pattern and then write your polynomial. Let me do that first. Okay. There's my function. So then f of 2 would be e to the 6th. I hope you agree. Okay. Then here's my first derivative. E to the 3x, but then don't forget that it's a chain rule, so times 3. So let me put that 3 here. Meaning that my first derivative at the point where I want to match at x equals 2 would be 3 times e to the 6th. Okay, all right, then let's just do one more just in case, so we can see a pattern. F double prime of x will be okay, 3e to the 3x, but then times another 3 for the chain rule. You know what I'm saying? So instead of this 3, let me just make that a 9. Well, I'll just show all my work actually. Times another 3, which is 9e to the 3x. Agreed? And so therefore, f double prime at the point where I want to match this function, f double prime of 2 would be 9e to the 6th. Yeah? Okay, and let me just make sure you get it. If I wanted to match the second or the third derivative at 2, let me not even get the general third derivative. The third derivative at 2, what's that going to be?
27 e to the 6th.
27 e to the 6th. Yeah, nice. It's just going to be the 9 times the 3, 27 e to the 6th. All right, that's the third derivative. What about the nth derivative in general? What's that going to be? How can I generalize the pattern for any n? What about, oh, yeah.
3 to the n e to the 6th.
Legend, yeah, that's it. It goes 1, 3, 9, 27. Those are the powers of 3 because you just keep multiplying by 3s to get that coefficient. So that's 3 to the n e to the 6th. Nice. Okay, cool. But that's just the pattern. That's just us getting into the problem. The actual answer for the problem would look something like this. It would look like polynomial of degree n of x would equal, remember the strategy is you want to match the function value, so that should be the constant term, plus this needs to be the coefficient of the first degree term. That way when you take the first derivative, that's the value of it. So in other words, this will be 3e to the 6th times x. Except that would be if it was centered at 0, but this one is centered at 2, so you need to shift it over by 2. So not x, but x minus 2. Okay, then the next term would be plus this dude needs to be my coefficient. For my second degree term, now when I take the second derivative, I get that as the coefficient, or as the second derivative. So that would be 9e to the 6 times x minus 2 squared. That's my second degree term. But then, do you remember that you're going to mess it up if you don't divide by 2 here? Because when you take each derivative, you're going to be multiplied by whatever power this is. So you need to divide by 2 factorial, technically. Yeah? Remember this? Okay. I don't know if I'm speaking another language or if you remember this. All right, let me make this small so I can fit my full answer. Okay, then the third term would be this 27, but let me just do a dot, 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 plus, dot, 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 plus the nth term is going to look like 3 to the n as the coefficient of my nth term thing, so x minus 2 to the n over n factorial. And it might take some thinking on your own about why this works again. Like you might have to go home and convince yourself that this works. But yeah, this should do it. This is the answer. And it's always satisfying when you do it in theory and then see it in real life, like see a graph of it. So watch this, you guys. Here's me going to Desmos. Let me have this open. All right, we said e to the 3x, and we're centering it around this point. Where is it? 403. Oh no, this might not work super well. Oh. Here, let's do it like this. Okay, that's pretty good. Okay, there's the real function that we're trying to match, and then here's our approximation step by step. We first said e to the 6. Let me actually call this the function. G of x equals e to the 6. Okay, it matches the function value, but nothing else. Then we wanted to match the first derivative, so we said, oh, let me put this as the term, let me think, or let me type it and then I'll think. Okay, I want to put this as the term in front of my first degree term. That way when I take the first derivative, it'll be equal to that. And so then my green function matches my red function, and the first derivative of the green matches the red. And then we said, okay, let me try another term. 9 plus 9e to the 6, x minus dose to the 2 over 2 factorial, which is just 2. Well, let me just write 2 factorial. Cool, and then it's now even a little bit closer. And then let's just do the third term and the nth term. Well, the nth term is not going to understand. The third term would look like 27, e to the 6 times x minus 2 to the third over 3 factorial. Over 3 factorial. And you can see it's a little bit better. It's hard because the graph is so big that you can't see really how close it is. But it gets a little better and better each time you add a term, as you saw yesterday. Cool! You guys learning? Okay. Alright, next one is for sine of x, and that one will be better to show you on the graph if we have time. Let me move this dude, make this big. And it says find the MacLaurin polynomial degree 5 for sine of x. Maybe you guys should try this. But notice it didn't give you a center because it specified that it's MacLaurin. So do you guys remember what that means about where your centers? Okay, nice. Yeah. Cool. Okay, so you guys try this. This is 5 derivatives that you have to match, like a polynomial of degree 5. You guys try that.
It's on the same as 0.
Right.
Okay.
Yeah, it's just like completely foreign. But the idea is basically do what we did up there, find f0, f prime 0, etc. And then there, yeah. So if it says one coordinate, it's all 0. Around any other coordinate. So at least do that part first. Find the function value first for second derivative, and then I'll show you how to do the polynomial. Nice, yes. Okay, if you need some guidance, you're trying to check the first few steps, there's that. And then if you need to finish it from there, here's like 20 more seconds. Nice. Nice, yeah. I'll start setting up the Desmo. Okay. So it should look like this. 0 for the constant term. 1 for the linear term. When you take the derivative, it'll match the first derivative. Then 0 for the second degree term over 2 factorial technically. And then minus 1 x cubed over 3 factorial plus 0. Oh no. Oh no. Okay, plus 0 x to the 4th over 4 factorial. Obviously, you don't have to write those. And then plus 1 x to the 5th over 5 factorial. Or if you want to write it nicer, this would just be x minus x cubed over 3 factorial plus x to the 5 over 5 factorial. Okay, cool. Hopefully that makes sense. And then here's us checking how close that is. So there's The first degree polynomial matches it kind of a little bit around the 0. Then the third degree polynomial. No. It matches it a little bit closer, and then the fifth one matches it really close. And you can see if you were to keep going to the 7th and the 9th and etc., it would get even better and better and better. Cool. All right. Questions so far? This is like the hardest part of the whole curriculum probably, is this idea. Question.
On the AP test, if they ask me this, can I just write like exactly what you wrote, or do I like don't have to apply it at all?
No. Oh yeah. No. You could write this whole thing. Yeah, that's good. That's a good question. Anything else? Yeah. Hopefully, as you do these, it's not like super crazy. What gets harder is the next section when it asks you when does this converge. Like, well, you'll see later. You'll see later. Don't start freaking out yet. It's not that hard. This one looks like it's intense, but it's not that hard. So what time is it? 24, and we have this and one more to do. Yeah. Okay. So I think you guys could handle this one. It's kind of a good question. So it gives you this graph, and it says h is the integral of that graph, and now write a Taylor polynomial for h. But treat this like any other. Treat this like the other ones that you've done. You guys try that. Actually, I don't have an answer yet, so let me get that. Like I said, if you're making 0 progress, just treat it like the other ones that you've done. Find h of 2, h prime 2. Nice, nice, nice. Oh yeah, you're right, I'm wrong. Good job. I forgot the center minor 2. Good job. It's like 20%.
The green one. Yeah.
I think I gotta check the thing. Yeah, it's the biggest. It's one of the biggest and integral. Yeah, both. Well, let me pull it up.
You're Dennis, you're saying that I know you're lying.
I used it. I understood the derivatives of or oh, they're metric functions.
Oh, it's centered at 2. Yeah.
Oh my god. Wait, there it is. No. There it is. Yeah, look, both of them. Okay. Should we go over this? You learn ready? Okay. For people who asked, it's like, this is a huge part of the test, Unit 10 is, and so is Unit 6. Which was integrals. Okay, h of 2, again, if you just find all three of these, then it's like treat it just like all the other ones that you've done, and it's not that hard of a question. So h of 2, it told you what it is. It's the integral from 5 to 2 of f of t dt. And to get that integral, well, what do you say this was? What was this?
67/8.
What did you say?
Negative 67.
Good job with the negative 67/8, because why is it negative?
Because it's like gone from 5 to 2 instead of 2 to 5.
Yeah, 5 to 2 instead of 2 to 5, so you have to make it negative. Nice. Then h prime of 2, what do you say that was? Or how do you find that? I know, I saw it on a bunch of people's paper. How did you get it, James?
Well, h prime of 2 is just f.
Nice. Because h is the integral of f, therefore the derivative is the function itself. So h prime of 2 is f of 2, which is, what was it, 3, that the function value, 3. And then h double prime would obviously be the derivative of h prime, which is f prime of 2. And this one is a little bit tricky. How are you supposed to find that?
Look at the graph.
And what about it?
There's a slope. It says it's 1.
Yeah, that's why they gave you the tangent line with a slope of 1. So f prime of 2 must be 1, the slope of the tangent line. Okay, cool. And then you put all this together and you say the p2 of x for this function would be negative 67 over 8 plus 3 times x minus 2 over 1 factorial. And then, I'm not even going to write that. And then plus 1 times x minus 2 squared over 2 factorial. Or just 2 if you want. Nice, y'all. Cool. Okay, and then this last thing is an important thing, but it's a little bit confusing, but hopefully not that much. So the thing that's confusing about it is that, like, okay, we just saw that we use 2 terms that, well, a second degree polynomial to approximate that function. And what this next little page tells you is how far off could you be only using 2 terms instead of an infinite number of terms. Like only matching 2 derivatives instead of matching every derivative thereafter. How far off could your approximation be from the actual value of the function? Okay, so I think for right now, let me tell you this, and then I'll get into the details as we do a problem. But do you guys remember? Well, let me check if you remember. For alternating series, remember when we were doing alternating series, plus, minus, plus, minus, plus, minus? We said if you approximate with the 6th term, for example, then what will be the error in the full series? Did you remember that? You remember? Yeah, it'll just be the next term. Okay, the oversimplified version of this Lagrange error bound for polynomials is that if you use 6 terms, the error will be kind of the 7th term. So you can just kind of think about it as an alternating series error bound, but there's a little caveat that it's really, what it actually says is it's not exactly the next term in the series, but rather the biggest that you could ever make that 7th term. I don't know how I should have thought of a better way to write that. But I'm saying this just tells you this is just the biggest that the next term can get. So make the next term as big as you can make it, and that's your error value, basically. Okay, what am I talking about? Well, here, let's do an example, and then I think you'll understand. Watch this. The function f has derivatives of all orders. Assume that f of 2 is whatever f prime, f double prime, f triple prime. Write a third degree Taylor polynomial for f about x equals 2, and use it to approximate 2.3. Okay. So this part I think you've had enough practice with that we could go through it fast. Third degree Taylor polynomial would look like p sum 3 of x equals match the function value plus the first derivative with the linear term minus the second derivative with the quadratic term plus the third derivative with the cubic term. Okay, there's my third degree Taylor polynomial. And then it says use that to approximate f of 2.3, which I think you can guess, like you've done this before with just tangent lines, but now you're doing it with higher degree polynomials, where you just plug in 2.3 into this approximation polynomial rather than with the function itself. Okay. And then if you calculate this, oh rats, I didn't do it because I was here late. If you calculate that, we're gonna have to just do it ourselves. Let's see what you get. 6 plus, because you need it for the later question, is like what is this value as a decimal? Okay, there it is. 6.921. Cool. Okay, and then the next part says that the fourth derivative, the biggest that could get, is 9 for every x in the interval from 2 to 2.3. Okay, and then it says use this information to find a bound for the error in the approximation of f of 2. Like for this, like how far off could this be from the actual value of f of 2.3? So this is what I was talking about before. Within your interval from 2 to your approximation, from 2 to 2.3, you have to check what's the biggest I can make the next term, which is why I told you this inequality. And then that will be your error for the whole series. So here's what I mean. Oh no, we're running low on room. Let me make this small. Put it up here. Okay. So part B says, okay, what's the error, how far off could your approximation be from the actual value? And like I said, you're just checking what the next term is, kind of, in a way. Really what you're checking is how big could the next term get? So what I'm saying is the error has to be less than the next term being fourth derivative at 2, well, at some z value times x minus 2 to the 4th over 4 factorial. So all I'm saying is, this is what I store in my brain, is I just put the next term on there, and then I worry about how big could I make this. So this is my next term in the series of the in the Taylor polynomial. Then I'm like, okay, how big could I make this? Well, this is already fixed because I'm plugging 2.3 into it, just like all these other ones. So the only thing that's changing, is this fourth derivative part, And I don't even know what the fourth derivative is, but luckily they told me that the fourth derivative can only get as big as 9. So the biggest I can make this whole term is 9. That'll be my error. Like if I put a 9 in here. And then I think we need the decimal, like the decimal equivalent of that. So let's find out what that is. That is 9 times 2.3 minus 2 to the 4 over 4 factorial is that much, 0.00303. Oh. We really only need 4 places, but just to be safe. Cool. So if you didn't catch that, one more time, this was our approximation using 3 terms. The fourth term, the biggest you can make that fourth term will be the error in the whole full thing. So the most I could be off is by that much, the thing I just drew an arrow to. Cool. And then it says, now, if I really wanted to find the actual value of f of 2.3, could that be equal to 9.22? And could it be equal to 9.27? And so all I'm going to do is take my approximation, add my error, or is it subtract? No, it's add because these are both bigger. Take my approximation, add my error, and see if that falls within the range. So let's check. 6.921 plus 0.003. Well, let's just do the full thing. What's that equal to? 6.925. You know what I'm saying, or did I do it wrong?
Do you want more?
Well, 03, I guess.
No, like it's 6.2. Wait.
6.924. Good job. Nine two 403. Okay, so according to my error, f of 2.3 could be this big. So maybe a better way to write this would be you can do this on your papers, right? You could say f of 2.3 is at most this big according to our error. And 6.22 is within this range, like it's less than 6.924. So yes, it could. F of 2.3 could equal 6.922. Since 6.922 falls within the error belt. All right, and then just to finish without going over time, could f of 2.3 be equal to 6.927? Let me ask you. Okay, good job. It could not be because the biggest the f of 2.3 could get is 9.24, not 9.27. So for part D, no, f of 2.3 cannot Nice. All right, we did it. Okay, so there's only one example on the notes of this Lagrange error bound, but it's pretty, like they tend to ask about it every year. Either what I've noticed is that on the AP test, they alternate between asking about the Lagrange error bound and the alternating series error bound, then the next year, like 1 year Lagrange, next year alternating series, next year Lagrange, next year alternating series. So you do have to know it. But obviously that's not an exact science. Sometimes they might ask 2 years in a row of Lagrange and then a year of alternating series error bound. But yeah, you have to know this. Make sure you do. There's a lot of problems on your homework about this, so you can practice it. All right, that is all from me, you guys. Tomorrow, no class. Wednesday, no class. But Thursday, yes, and Friday, yes. And hopefully we finish the packet by then.
Yeah.
All right, y'all. Good